Monday I am going to give you on which sections should focus more on. Okay. So there are many topics covered in the second half of the course materials, especially chapter important chapters, which is the second half of chapter 4 and chapter 5, and I will be covering chapter 7, then we will finish chapter 7 today. And on Monday, I'll try to finish chapter 8. So as you can see, in one lecture, I can finish one chapter today. Let's see how far we can cover, and then I'll give you some hints on that. So, part 2 of our course materials is about statistics. See, the title of the course is Probability Statistics Random Processes. So we did finish the probability part, which is chapter 1 all the way to chapter 5. Statistics is going to be chapter 7, chapter 8. These two chapters will cover. Of course, I said 2 chapters, but I'm not going to cover all the sections of these chapters, only the sections that I have in my slides. I will just go through those sections of statistics part. Just the fundamentals of statistics, and we'll have computer experiment related to statistics. And then chapter 9 and chapter 10 is about random processes. Chapter 9, chapter 10. Again, chapter 9, chapter 10, I summarized. I'm going to give you a summary of chapter 9 and chapter 10 through practical problem. So this is random processes. So let's say about statistics. So statistics starts with the idea that so far we did assume that we know the probability models. Either we know the probability mass function of a discrete random variable, either we know the probability density function of a continuous random variable, or we know the cumulative distribution function of a continuous or discrete random variable. So we know all these probability models. Given these probability models, we can determine the probability of certain event. From now on, we will not assume any probability model. From now on, all what we know, that's the main idea. All what we know is some data, some measurement data. We'll take some measurements. We'll take some measurements. We'll take some raw data. Based on raw data, we'll come up with some probabilistic decision, probabilistic measure. We'll have some probabilistic metric. So that is the key idea of this chapter of statistics. In practical situations, probability model, probability distribution may not be known, but what we do, which implies that we rely on some data, raw data. So we use raw data. Very important, raw data. We absolutely have no idea about the data, so we just have some raw data, and then use this data to infer some meaningful information. So that is the idea behind this part, second part. So problem of counting number of occurrences of events, measuring cumulative effect, and averages of series of measurements can be reduced to finding distribution of random variables, that is sum of n random variables. So sum of n random variables, that is also key terms here, sum of n random variables. In other words, what we are going to see that instead of what did we do previously? We had a random experiment. We had a random experiment, and we keep repeating that trial, random experiment, random trial. We keep repeating. Okay, but we have for one random variable, for one random experiment, we can have one random variable, or two random variables, or three random variables. But here, what we are assuming is, so please don't get confused, that, okay, so we run a random experiment, we give a trial, and we take the measurement, and this measurement could be anything. So we can think of this random variable as one random variable, okay? Now, we are going to move on to the next step. Again, we take the measurement, we take into account this is another random variable. Again, we go to the next step. This is another random variable, and so on. In the practical situation, for example, you what you do, you take measurement, you take voltage measurement of between two terminals of your circuit, for example. That voltage measurement, you take the measurement once, okay? That measurement itself follows a distribution. So that measurement could be like, can follow a Gaussian distribution and so on. So, or Gaussian distribution, or classical distribution, or binary distribution, or whatever distribution. Okay. Now, you take the second measurement itself follows another distribution. That distribution you do not know, but you do take measurement. But the point here is that at each step, you take the measurement, you treat the measurement as a random variable. Okay? At each step, you treat the measurement as a random variable. So that's why this random variable is very important. Now, the other key terminology here, so I have n trials, we have n random variables, x1, x2, dot, xn. So the other key terminology is this one, independent and identically distributed random variable, IID. So if you just, this is very, very common term in probability theory, IID. If you do research in certain labs, in operations research, or related to decision making, okay, or even stock market, I should not say this stock market word, but probability theory is heavily used in stock market. Okay, so now if you simply type IID, okay, it's so popular and so IID, I dot I dot D dot. Okay, you see that IID, if you simply type IID, people also write IID, independent and identically distributed. Independent and identically distributed. Very, very common terminology, but you will need to know the physical significance of this IID, independent and identically distributed. When you say independent and identically distributed, what you do, okay, think of this variable as follows. Okay, this is what many people assume, and that's the way to go in case you want to know about a random variable that you have no idea about its distribution. But you do start with this IID. IID means that you take a measurement, you assume a distribution of this random variable, and the mean and variance, you record the mean and variance of this measurement. Now you have one step forward. Now you take a measurement. Okay? You take a measurement, and this measurement itself is a random measurement. But if you take many measurements at this step, in that case you will see some mean and variance for this measurement. Okay? You go one step forward. Okay? You again take measurement. This measurement itself is a random variable, x3 for example, and that has mean and variance. So IID means that doesn't matter how many measurements you take all the way, and each measurement is considered as a random variable. In each random variable, you will have in each step for each random variable, step 1, step 2, step 3, for each step you will have same mean and same variance. That is the key idea. So IID means that does not matter how many measurements, how many random variables you have. So what you have here is that the mean of x1 will be mu, mean of x2 will be mu, and dotted, mean of xn is going to be mu. So all these means are same. Similarly, the variance of x1 equals variance of x2 equals dotted, variance of xn is going to be sigma squared, which means that all random variables will have same mean and same variance. And that way you can say that these random variables are IID, follow IID behavior, which means that these random variables are independent and identically distributed. Very important, this idea. So now we assume that, okay, these random variables are IID. Now let's see if random variables are IID, what is the behavior of sum of random variables. So this is one random variable, this is another random variable for another trial, and we have n trials. So total you have n trials of random experiment, and then in each trial you have n are these random variables. Now what we are trying to accomplish here is that we are going to sum of all the random variables x1, x2, xn. So Sn equals x1, x2, xn. You sum them up, and then, okay, guys, let me know. Okay, if you have x1 is a random variable, x2 is a random variable, x sub n is a random variable. Is S sub n, my question to you is S sub n, is it a random variable? Yes or no? We have x1, x2, x sub n. All these are random variables. We add them up, and we call it S sub n. My question to you is S sub n a random variable? Yes or no? Yes, it's trivial, like, because these are random variables, so these are random measurements, so therefore S sub n is going to be random as well. So it is a random variable. Okay. Now I take the expectation of this random variable. Expectation of this random variable is going to, because it is linear, you apply expectation operator in x1 plus expectation operator in x2 plus plus expectation, you apply expectation operator in xn. Okay? So in other words, you can actually write the right hand side in the form of summation as such. So therefore, expectation of the sum of random variables, sum of n random variables. I did not say IID yet. Here I started with sum of n random variables. I did not say these are IID yet. Okay. So if we do not assume that these random variables are IID, we did not assume. Now this is the case. So basically, because we did not assume that this expectation is going to be mu1, this is mu2 mu sub n. And if it was IID, all these mu's would be the same mu. So because we did not assume that, then sum of mean of sum of n random variables, in other words, the expectation of, we denote it with mu of Sn, mu of mean of or expectation of sum of n random variables is basically mu1 plus mu2 plus plus mu sub n. In other words, you can write it j equals 1 to n mu sub j. Okay. So that is the mean. What about the variance? The variance here the variance here is variance of random variable Sn, which is the sum of n random variables, is given as such. So you have j equals 1 to n, variance of xj. Now you have this double summation. So let's say you have two random variables, x1, x2. So what you do, you have this equation for n equals to, if this equation is going to be variance of x1 plus variance of x2 plus covariance of x1, x2 plus covariance of x2, x1. That's what this double summation means. Okay, so using this double summation, you see for n equals to, you have these two quantities. You see that. Okay. Okay. Now let's solve this example. So this example, given this theory, this example, it's a piece of cake. Okay, in this example, okay, so find the mean and variance of sum of n IID random variables. Here, in this example, it says that IID random variables, and each with mean mu and variance sigma square. Okay, look, you have Sn equals, let Sn equals x1 plus x2 plus dotted plus x sub n, and you want to find the mean and variance of sum of n random variables. Okay, so what you have here, mean of Sn, which is basically expectation of Sn, equals what? And variance of Sn, which is variance of Sn, equals sigma Sn squared equals 1. Okay, you can just denote this using mu sub Sn equals 1. Okay, since different color, since x1, x2, dotted xn are IID are this. So you have expectation of x1, which is mu of mu1 is mu, expectation of x2, which is mu of mu2 equals mu. So same mu. And all the way expectation of x sub n, which is mu sub n equals mu. So all of them are same. So which implies that mu1 equals mu2 equals dotted equals mu sub n equals mu. Now let's talk about variance. Variance of Sn equals variance of x1 plus variance of x2. So actually, let's determine the mean first completely. So therefore mean of Sn, which is basically expectation of S sub n, which is basically mu sub Sn, we denoted with that, and then it's going to be mu1 plus mu2 plus dotted plus mu sub n, which is basically mu plus dotted plus mu. What is the result, guys? What is the result? Mu sub Sn, mu plus dotted mu. What is the result? How many mu's? N? N times n. N times mu. Yeah. N mu. So this is going to be one result. Now let's talk about variance. Okay, variance, we are going to apply this formula. Okay, because it's independent and identically distributed. Because the random variables are independent and identically distributed, therefore the covariance of one random variable with other random variable, because these two random variables are completely independent. If these two random variables are completely independent, then their covariance is zero. So if the covariance is zero, this double summation, entire double summation, disappears completely. So the entire double summation is going to be zero, because this covariance is going to be zero, because all the random variables are IID. Therefore, their covariance is zero. So therefore, the variance of Sn, which we denotate with sigma sub Sn squared, is going to be variance of Sn, which is sigma sub Sn squared, is going to be summation j equals 1 to n variance of xj squared plus summation j equals 1 to n, k equals 1 to n, and j not equals k. In that case, you will have covariance of x sub j comma x sub k. Since RVs are in IID, covariance of x sub j comma x sub k equals 0 for all j and k and j not equals k. So in that case, that is the case, and variance of x1 equals variance of x2 equals dotted equals variance of xn is going to be variance of x, which is simply sigma squared. Let's call this sigma squared. So this is known. So mu and sigma squared, this is known. So therefore you have sigma sub Sn squared is simply n sigma squared. So this guy is known. So variance of x, guys, there is no square here. Variance of x, variance of x1, variance of x2, dotted, variance of x equals sigma squared. So you will have n sigma squared in total. So that is the answer. So we have variance of the sum of n IID random variables is simply n sigma squared. Now sample mean. Okay. Sample mean. Now given the theory that we have, now sample mean is a piece of cake. So sample mean is, you have the sum of n random variables, you simply divide it by n. That becomes sample mean. And sample mean, because the sum of n random variables is a random variable, sample mean itself is a random variable. That is important. So sample mean is basically sum of n random variables, which is Sn divided by n. So this sample mean itself is a random variable. So make sure you don't get confused that this mean is constant. No, this mean is not constant, because this sum is variable, is a random variable. Because this sum is a random variable, that's why this sample mean has to be a random variable. So make sure, that's where people make mistake, that usually when they see that okay, mean is constant, but it is not. Here, because the sum, the addition of all the random variables, which is also a random variable, when you divide it by the number of random variables, then because of the summation, which is a random variable, this mean becomes a random variable. In case, okay guys, what was the expectation of Sn, which is we just derived, we just solved this example. What is the expectation of Sn when Sn was sum of n IID random variables? It was nv, right? You remember? We just got this example. We just got this example. So expectation of Sn is nv. Okay. So now what I am trying to say is that because the expectation of Sn is n mu divided by n is constant, so it becomes n mu over n. So n disappears, you are left with mu. So therefore, the expectation of the sample mean, so this is your sample mean. Sample mean. So the expectation of sample mean is mu, which is the mean of one random variable. So in other words, this sample mean is called unbiased estimate of mean. Now, how to come up with the variance of sample mean? We came up with, in the previous example, we came up with mean and variance of sum of n random variables. Here, in this slide, here we are talking about sample mean, which means that we are trying to find the mean and variance of sample mean. Previously, we found the mean and variance of sum of n random variables. Here, we find the mean and variance of the sample mean, which is itself is a random variable. So sample mean has a variance. So if the random variables are IID random variables, sample mean, the variance of sample mean is basically the variance of one random variable over n, which is sigma square over n. Okay? So that is the result that will be used. So clearly, when n goes to infinity, which means that you have n infinite measurements, then the variance of sample mean goes to 0. So which means that the mean is going to converge to true mean, and sample mean converges to true mean, and variance is going to be variance of the sample mean is 0. Okay. What does that mean? True mean. So let's say entire population. I'm talking about this class. Okay. I'm talking about this class. Entire population. I'm talking about this class. Now, what I'm going to do? I'm going to calculate the average age of this table. Okay. Let's say what's the age. So that's it. So I'm going to calculate the average age of this table. So that is one sample mean. Sample average. Okay. So I'm going to calculate the average age of this table. Let's say average age is 19 years old. Average age, which is the sample mean of this table, is let's say 20 years old. Average age is let's say 18 years old. Okay. So average age of this table is, let's say, 21. Okay. So average age of this table is like 15, 67.
Yeah.
Okay, I take it 67. Okay. Okay. So I got all these averages. Okay. All these averages. Now what I do? So I took the sample averages. These are sample mean. You can think of these as sample mean. As he said that 67, I can just calculate it and it becomes random and it becomes probably like 18.5 years. Okay. Okay. Now what I'm trying to say is that so we took sample averages. Okay. This sample average for each table is not the true average. Is not the true mean. Okay, of the entire population. As I said that entire population, I'm talking about this entire class. Okay, so is not the true mean. This sample average is not the true mean or true average. Now, what I do, I took these samples. Now I take, when I take the average of entire class, that time I get the true average, right? That's what it means, true mean. That's what this mu is. Okay, that's what this mu is. Now, this n is a sample number of samples you take. When n goes to infinity, which means that in the context of this class, when n, number of students, when I calculate the average, when I take into account the entire class, that time I get the true mean. So that time you will see that this sample mean boils down to the true mean. That's what mathematically it means. That samples, as we increase the number of samples, this sample mean converges. In other words, the technical term, it's not, I just said that sample mean boils down to true mean. The technical term is that sample mean converges to true mean. Sample mean converges to true mean. And that's what you see that's what you will see in laws of large number. So laws of large number say that when you start with some samples, as you increase the number of samples, you see that sample mean boils down to true mean. In other words, guys, the first computer experiment that you did, guys, do you remember the relative frequency? Do you recall relative frequency, computed relative frequency? Or you forgot completely? In chapter 1. First computer experiment. Relative frequency boils down to probability. You remember, guys? So relative frequency, which means that you take sample measurements and you compute the relative frequency. And as you increase the number of measurements, number of trials, number of measurements, you see that relative frequency boils down to probability. Here, after completing 6 chapters or 5 chapters, now we say that, now we can prove that, okay, so based on the samples, if we take the samples, we can calculate the sample mean, but as we increase the number of samples, then the sample mean becomes the true mean. Sample mean becomes the true mean. Okay. So now other concept is Chebyshev inequality. Chebyshev inequality, there is a math behind it, but try to understand the concept, the physical meaning of it. This Chebyshev inequality, what it says, Chebyshev inequality, what it says that how close your sample mean to your true mean. Okay? So what is the probability that the difference between sample mean and true mean is less than certain value, certain percentage. So we can, using Chebyshev inequality, we can actually determine how close the sample mean to the true mean. So the Chebyshev inequality is going to help us to determine this result. Okay? So we want to determine, this is basically your true mean, and this is your sample mean. So now you take the difference between true mean and sample mean. This is basically Do you know what is this? These vertical lines. What does that mean? These vertical lines. What is this? Absolute, right? Right? These vertical lines between a number. So -5 is basically simplified. You just don't care about the sign. So that's absolute value of certain number. So you take the absolute value of this difference, sample mean and true mean. You take the absolute value. That difference greater than or equals certain number, very small number. Usually this is very small. Less than or equals variance of the sample mean over this small number. So usually small, we choose very small number. And we see that sample mean minus true mean greater than or equals mu, less than or equals. This variance of sample mean is basically sigma squared over n, and it's basically because you have this epsilon squared. What is this symbol, guys? Epsilon. Epsilon. Okay? So the command you write is epsilon, as it is, epsilon. When you write it in Markdown, okay? The LaTeX command is epsilon. So epsilon squared, so which is nothing but variance of sample mean, which is sigma squared over n, and here you get epsilon squared. So now I want to make it greater than or equals. So if I make it greater than or equals, in other words, I want to minimize the difference between true mean and sample mean. Less than certain value. In that case, it becomes 1 minus sigma squared over n epsilon squared. This is also called weak law of large number for finite number of samples. For finite number of samples, this is called weak law of large number. Now let's go through this example where I utilize the Chebyshev inequality. Okay, in this example, what you have is you have a circuit diagram. You have a circuit diagram and you want to measure the voltage across this branch. And this voltage, true voltage is V. This true voltage we do not know, unknown. We do not know this true voltage. All what we know is that you have a DMM, digital multimeter. We have a DMM and we take the measurement, which is xj, for j equals 1, 2, dotted, n number of measurements. All what we know is some measurements. So we take DMM and we take multiple measurements. So what it says that a voltage of constant but unknown value is to be measured. Each measurement xj is actually the sum of desired voltage and noise voltage. So each measurement you have is, you can model this as a true voltage plus some noise. So this is your noise. So true voltage plus noise. So you add them up, you get the random measurements, which you do not know. But what you do know, this noise has this statistics, noise statistics. You know that the mean of this noise is 0, which means that mu of n j equals 0, and the variance, the standard deviation, which is sigma n j equals 1 microvolt. Okay, so you know the noise statistics, but you do not know what is the true voltage. All what you know is this measurement. So now you want to find the mean and variance of xj. Okay. Solution. Solution here is solution, which is first one, is the mean and variance of xj, which is expectation of xj, which is mu sub xj equals what, and you want to know the variance of xj equals what. So that's what you are trying to find. So x sub j, expectation of x sub j, which is mean of x sub j, is going to be the expectation of the true voltage, expectation of true voltage plus expectation of n sub j. And this is basically, okay, this true voltage, what is the expectation of true voltage V? What is the expectation of true voltage V? True voltage which is unknown. What is the expectation? But true voltage is unknown, but we know that it is constant. What is the expectation of the constant? What is the expectation of the constant? It doesn't change. It's constant. Okay, so the expectation of a constant is a constant. So expectation of V is V. And what is the expectation of Nj? We do know that noise voltage has zero mean. So expectation of this quantity is zero. So therefore, mu sub xj equals V. This is one answer. Okay. This is one answer. Now, what is the variance? Variance of xj is going to be variance of V plus variance of Nj, but Nj has zero mean and standard deviation 1, which means that the variance is 1. So what you have here is that, what is the variance of V?
V.
Yeah, V is constant but unknown. What is the variance? What is the variance of constant? What is the variance of 10? 0. Variance of a constant is 0 because you know the mean is constant.
Yes.
So mean minus that constant is 0. So the variance of constant is 0. So the variance of this guy is 0 plus the variance of this guy is standard deviation is 1 microvolt. So then the variance is 1 microvolt squared. So therefore the variance of xj is going to be 1 microvolt squared. So this is another answer. Okay, next is, well, we are going to apply the Chebyshev inequality, guys. So please pay attention, see how I explain. Here, what it says, that because we do not know what is the voltage, what is the true voltage. So the question here that how many measurements we need to take, so that the probability that the difference between true mean and the sample mean, so you take sample measurements. So how many measurements you take so that the probability of the difference between true mean and sample mean is, yeah, true mean is close to the sample mean is at least 0.99, which means that you are 99% sure that the sample mean, after, if I take this number of measurements, the sample mean is going to be 99% sure that it is close to the true mean. Did you understand the point here? That how many measurements you need to take so that you can be guaranteed, you can guarantee 99.99%, you can guarantee that if I take this many measurements, I calculate the sample mean, and this sample mean is going to be close to the true mean. Still you do not know what is the true mean, but at least you know that if I take this many measurements, you are 99.99% sure that it is close to the true mean. And that's what the Chebyshev inequality comes in. the next one is sample mean m sum n equals 1 over n summation j equals 1 to n, and it is expectation of it is x of j. So if you take expectation of m sub n is going to be b, and the variance of m sub n is simply 1 over n. Sigma squared over n, with sigma squared equals 1, it is 1 over n. Okay? So it's already 10:50. Do you have class after this, guys? I just right after this one?
Yeah, I did. 451.
4:51. Can you give me 5 minutes, guys? I just want to finish this example. So Chebyshev inequality using I have the formula already. Chebyshev inequality. We have the formula already, so it's in my slide. Probability that absolute value of mn minus b less than epsilon. This probability greater than or equals 1 minus variance of sample mean over epsilon square. We do not know this difference epsilon, we do not know, but what we do know epsilon is actually 1 microvolt. So epsilon is given 1 microvolt, which means that the difference between true mean and sample mean is going to be less than 1 microvolt. So epsilon given this epsilon equals 1 microvolt. So if that is the case, you say that this has to be greater than or equal to 0.99. In other words, 1 minus 1 over n greater than or equals 0.99, and you solve this inequality, you will see that n has to be greater than equals 100. So it is going to be 0. If you solve this inequality, it is going to be n has to be greater than or equals 100. So this is the end result. So number of measurements. So therefore, let's write the end result. So expectation of xj is b. Variance of xj is 1 microvolt squared, and n equals 100. So you need at least 100 measurements so that you are 99% sure. You are 99, you can guarantee 99% that if you take 100 measurements, the difference between true mean and the sample mean is going to be only 1 microvolt. Okay? So that's where this Chebyshev inequality comes in handy. So I did not go through the proof. There is a mathematical proof, but here we will be making use of, will make use of tertiary inequality to solve this sort of electrical engineering problem. Thank you guys, thank you for your time. So, you have a nice weekend.